That was when it came to me, that image of riding a beam of light.
This was the first of Einstein's famous thought experiments. He created deceptively simple scenarios to explore the most complex concepts. If light were a wave, he reasoned, then no matter how fast it travels, it ought to be possible to catch up to its peaks or valleys. But then Einstein wondered, what would he see? Would the light stand still? Would time stand still? Would he ride that same peak of light forever, a glimpse of one frozen instant? At 16, Einstein could not find the answer to his questions. He was not yet a trained scientist. Researchers tried to measure the speed of light through the ether, using the Earth as the laboratory. The Earth orbits the Sun at 20 miles per second, racing through the ether as it goes. That would set up a wind as the ether rushes past the Earth. And if light travelling through the ether matched ordinary experience, then a beam of light moving with the ether wind should move faster than a beam of light struggling in the opposite direction, against that 20 mile per second breeze. Unfortunately, every attempt to measure such variation in the speed of light failed. With every experiment, the speed of light remained rock steady. Which means, hard as it may be to believe, that time actually passes more slowly on the drive to work than it does while sitting at a desk. Lengths also shrink as speed increases. In a car travelling at 30 miles an hour, changes in time and length are imperceptible. But if you could drive at 90% of the speed of light, you would shrink to 44% of your usual length, from the point of view of someone watching from the side. And here, finally, was the answer to Einstein's first question about light. What would happen if he could ride a beam of light? Nothing, for he never could. At the speed of light itself, length shrinks to zero and time stands still.
It's called the principle of equivalence. Equivalence, that is, between constant gravity and constant acceleration. Imagine an experiment in which different objects with different masses all fall with exactly the same acceleration, called g. That might happen because the laboratory is on the surface of the Earth. But the same thing would also happen if the laboratory were far from Earth and everything else, say in intergalactic space. It would happen if the laboratory were accelerating upward with acceleration g. All the objects inside, obeying the law of inertia, would not accelerate. But they would all seem to fall with the same constant acceleration. No experiment of any kind, done entirely inside that laboratory, could determine whether the objects fall because of the pull of gravity or because the laboratory is accelerating upwards in outer space. The idea seems almost too simple to be true, but Albert Einstein didn't take it lightly. Instead, he asked how the experiment would come out if it were performed with a beam of light. With the laboratory out in space, the answer was easy to see. If the rocket accelerates upward while the beam goes straight across, it must seem to bend downwards, just a tiny bit. But then what would happen on Earth? The answer comes from the principle itself. Since no experiment, not even this one, can tell whether the laboratory is on Earth or in space, the result must be exactly the same. In other words, Einstein concluded that light doesn't travel in straight lines. Instead, it bends ever so slightly because of the gravitational force of the Earth.
In his old thought experiments, Isaac Newton had shown that gravity governs the motion of the solar system as well.
But even Newton's theory could not explain how gravity exerts its influence throughout the universe. That was the mystery of gravity. How is it that the heavens stay on track? What is it that orders the universe as a whole? In another of his thought experiments, Einstein put the idea this way. He asked, what if someone were in an elevator when the cable snapped? He would float, weightless, as he and the elevator both free fall at the same rate in the Earth's gravitational field. Then Einstein changed the scene. What if the passenger were in a rocket ship far from Earth? He would still float with no gravitational field to hold his feet to the floor. But what would happen if the rocket began to move? As it accelerates, the floor of the rocket rises. On its way up, it would catch the passenger, and to him it would seem that gravity was holding his feet to the floor. And if gravity and acceleration feel the same, perhaps they are the same, and there is no difference between accelerating in outer space or standing in the Earth's gravitational field waiting for the elevator door to open. This was classic Einstein. His contemporaries found this equivalence of acceleration and gravity interesting. Einstein now asked, if acceleration and gravity are equivalent, what happens while accelerating that reveals something new about gravity? Back to his rocket ship, Einstein resumed his thought experiment. As the rocket accelerates, a ray of light shining through the window hits the other side at a lower point than it entered. To a passenger, the light appears to curve. If acceleration can bend light, then by the equivalence principle, gravity must do the same. It seemed a crucial clue. But where would it lead? Space-time without matter is flat, but add a rock or a star and the whole picture changes. The enormous mass of the star creates a huge dent. Anything that passes close enough will roll down and around that warp in space-time. That's gravity, the straightest path through the curves in space-time created by matter and energy. It was this picture that showed Einstein how gravity holds the Earth in orbit. The Earth simply follows the warp in space-time created by the Sun. It took Einstein 3 years to master all the subtleties.
Let's see where he introduces this first.
By the fall of 1915, he was ready to put the theory to the test. The orbits of the planets were understood with extraordinary precision, with one exception. Mercury's orbit shifted slightly, unaccountably, every year. The calculation vindicated Einstein's radical idea that space-time is curved. Mercury, the innermost planet, shifts its orbit as it travels around the dent in space and time created by the Sun's huge mass. Mass everywhere deforms the space around it. Even light, as Einstein had recognized years before, must follow all the curves in space and time, mapping the shape of the universe as a whole. It is this understanding that drives the scientific story of creation. The Big Bang, the expanding universe, the structure of galaxies, the great sweep of modern cosmology derives directly from this single equation. Space and time on the left, matter and energy on the right. This is the general theory of relativity.